Okay, so looking at this packet, we're going to start on number 31. So for number 31, how many amps? It's the one that has all the measurements on front. So this one. Okay. Yep, so problem number 31. 4 amps, good. 32? Careful. We've got 12 volts. We've got 24 amps. So 12 volts equals 24 times what for R? Oops. To solve for R, we got to divide by 24. What's 12 divided by 24? 1/2 or 0.5 ohms, yes. Number 33, how many volts? 18 volts, 34. 6, perfect. 36, 7 total amps, okay. 4 and 3, perfect. Is that what you got? Good. 37 is a little bit trickier. 2 amps and 9 ohms, and of course, how many volts? 18, good. You guys both came up with that? Good deal. Number 38. 8 amps, 2 ohms, and 6 ohms. Works for me. 39, you've got the 8 amps. The other amps has to be 5 and 3, yep. 3 ohms and 5 ohms, perfect. So if you look back at number 36, what's the total resistance there have to be? Careful. You have 12 volts and 7 total. Easier to figure out, just use your total voltage and your total current. Yeah. 12 divided by 7, right? So it's 1 5/7, or 1.714285743 approximately. Yeah. So you got 1 5/7 ohms is your total resistance. What is the total resistance in 37? 4.5, you got it. Have you guys gone over that with a parallel circuit? Yeah, if they're both are the same, it's just going to be half of the resistance. Yep. How about for number 38, total resistance? $1.5, very good. And for number 34? $1.875 works for me. Did I say 34? 43 it should be, sorry. 43 is circuit number 39. Okay, so now down in the last 4 down here, 44 through 47. Three amps, yep. 45. 2 ohms, very good. 46. Should be 55. 5 amps times 11 ohms. Now the other one here, of course the amps is going to be 6, right? The amps are going to be 6. So 24 volts. Yeah. So any questions on those? What's that last one? Yeah, you just know since it's a series circuit, the current through one resistor has to be the total current through the whole circuit. Yeah. Okay. I also gave you a worksheet. Where is it? It says parallel and series circuits on it. Kind of like this is the one from last Thursday.
Yeah.
I'm just going to do like one problem off of each section here. Oh, it's just a single sheet.
What was the last thing that you were going over?
There was that first packet from last Monday. The front of it looked like this with all the measurements on it. Okay. So the parallel and series circuit worksheet. I'm just going to do like number 5. Number 5. So 4 milliamps and careful. If you got 6 volts, 4 milliamps is 0.004. The resistance has to be 1.5, bless you, 1.5 kilo ohms. Did you guys go over scientific notation at all? A little bit. So the way you look at this is 6 volts equals 4 milliamps times our resistance. Milli is 10 to the negative 3. Okay, so now when we multiply this, 2 things have to happen. The 4 times whatever this is has to multiply to make 6. And the 10 to the negative 3 and whatever this is has to multiply to make nothing. Well, it has to be 10 to the negative 3 times 10 to the positive 3. That'll cancel out. 4 times 1.5 makes the 6. So it's 1.5 times 10 to the third, or 1.5 kilo ohms. Does that make sense? It's kind of a roundabout way of going about it. Okay, so let's jump down. Let's do number 10. Our series circuit. All I asked you for was, I said the resistances are equal there. We'll do number 10, then we'll do number 9 as well. So for number 10, the total resistance has to be what? So 12 volts equals 200 milliamps, right? 30 each. That sounds about right. So we've got 200 times 10 to the negative 3. So this has got to be 10 to the third again here, right? But 200 times what makes it 12? 0.06.
Did you think of that in your head?
That? Yeah. Calculation is all about patterns. Once you see the number patterns, the calculations are pretty easy. Now, of course, when this is 0.06 times 10 to the third, we listed as 60 ohms. So you're right, 60 total, 30 each for R1 and R2. The other way is you could have just listed this as 12 equals 0.2 times R, dividing by 0.2, that has to be 60. Let's jump up to number 9. Number 9 is a little bit more complicated. So for number 9, we're given the voltage is 6 volts. The next useful piece of information we're given is that the power is 3 watts. What's that tell us about the current? Current has to be 0.5 amps. Perfect. Because 6 times 0.5 makes 3. Remember, power is current times voltage. So now that we have 0.5 amps, What's the resistance have to be? The total has to be 12, so R1 is 4 ohms. You were correct. Because 12 minus 8 makes 4. Any questions on any of the other problems on the front side of this that you want me to look at? Okay. Back side with the parallel circuits. Let's do number 15. So for number 15, we're given that the total current is 2 amps. We're given that R1 is 12 ohms. We don't know R2. We're not given I1 or I2. We are given P total is 24 watts. What's that tell us about our voltage? Must be 12 volts, because 12 volts times 2 amps gives me 24 watts. So once we know that it's 12 volts, we know that I1 must be how many amps? 1 amp. Because if R1 is 12 amps, or 12 ohms, 12 volts over 12 ohms is 1 amp. So that means I2 must be 1 amp, because I1 plus I2 has to give us I total of 2. If those currents are the same, the resistances must be the same. If the resistances are the same, then of course the power gets split 50-50. So each resistor dissipates 12 watts of power. Any questions? All right, let's move up. Let's do number 14. That's a little bit more interesting. So for number 14, we're given the voltage is 12 volts. You are given R1 is 40 ohms. R2 is 60 ohms. And that's it. What's our total have to be? 24. Very good. So if our total is 24 ohms, total current is half an amp. Yep. Current 1. What's that? 0.3. And current 2. 0.2. Very good. You look confused. You look confused. Or just deep in thought. Oh, gotcha. Okay, so power total, of course, would be 6 watts. Power 1. What's that? 3.6, yep. And power 2, 2.4. Any questions? Okay, now the last two I said are extra credit. Did anybody do them? No? Yeah, let's do them together just to see how you did. Not sure if you got them right. Well, you tried. So for the first one, we're told this is 12 volts. And we're told this is 4 ohms, 12 ohms, and 24 ohms. Which makes the equivalent resistance here how much? 8 ohms, right? 1 over 12 plus 1 over 24 is equal to 1 over 8. So if that's 8 ohms, then the total resistance here has to be 8 plus 4, because they're in series now, right? It's 12 ohms. Which means that the total current is 1 amp. Which means the voltage dissipated here is 4 volts, because 1 amp over 4 ohms. Which means across here we have 8 volts, which makes this one 8 over 12 or 2/3 of an amp. And this one, 8 over 24 or 1/3 of an amp. 4 volts times 1 amp makes this 4 watts here. 8 volts times 2/3 of an amp makes this 5 1/3 watt here. 8 volts times 1/3 amp makes that 2 2/3 watts here. Of course, the total produced, 12 volts times 1 amp is 12 watts produced. And that looks like it adds up. Did you get that one right? Cool. For 17, you're given that the total current is 2. So that tells you the total resistance has to be 12 ohms. Which means R1 has to be how much? Did anybody get R1? For number 17, did you get R1?
Yeah, but I did it wrong.
Okay. I'll see if you make sure I did it right. It gives you that this is 24 volts. These reach 14, right? Those reach 14, that means the equivalent is 7. If there is 2 amps of current, 24 divided by 2, there's 12 ohms total. So if this is 7, this has to be 5. And I'll let you guys take it from there. Okay, so our new stuff for today, we want to talk about proportions. If we have ratios that have to be equal, let's say I know that I need a 2 to 5 gear ratio. I have to speed up a motor. So whatever I'm powering has to turn faster than the motor does. So I'm putting it on a 2 to 5 gear ratio. And I have a motor that has 20 teeth on it. How many teeth do I need on the other gear? Well, the 20 goes with the motor. And if you recall, on a gear ratio, the motor is the bottom gear. And that's the driving gear. So the 20 teeth goes down there. Find out how many teeth you need on the other gear, you cross multiply. 2 times 20 is 40, and you divide by the 5. So divided by 5 is 8. So there's 8 teeth on the other gear to keep that ratio. Does that make sense? Now when I set these up, there's a lot of different ways I can do them. For example, probably one that's the easiest to show is if I have a slope. Let's say this roof, this symbol here means 512 slope. That means that there is 5 feet of rise for every 12 feet of run. So if this roof has a span of 36 feet, and I want to know how high this is, the height of that. You can call that H. I could do, that's a 512 slope. I do 5 over 12 as my slope ratio equals what's my height, goes with the 5 because that's vertical. Now it's not going to be 36, of course, it's going to be 18 feet, goes on bottom here. Across multiply and divide, I get my height is 7.5. But that's not necessarily the only way I can set up that ratio. I mean, the 5 and the 12 go together because they both describe the slope. H and 5 go together because they both describe the vertical. 12 and 18 go together because they both describe the horizontal, the run and they're both runs. But I could have done this. 5 is to h as 12 is to 18. Notice the 5 and the 12 are still together. They're just on the horizontal axis instead of vertical. And the h and the 18 are still together. They're just horizontal instead of vertical. And the 5 and the h are still linked together. And the 12 and the 18 are still linked together. In a proportion like this, it's the relationships that matter, not where they're at. As long as I maintain those relationships, it's still a valid proportion. Notice if I go to solve this, I'm still going to cross multiply 5 times 18 divided by 12, just like here was 5 times 18 divided by 12. I can flip the proportion over. I can do h over 5 equals 18 over 12. Guess what? When I multiply, I'm still going to multiply 5 times 18 divided by 12. So there's not just one correct way to set up these proportions. The key is to maintain the relationships. So like for you, if you're looking at a transformer, and let's say you need to step from 10,000 volts down to 500 volts. Well, you could either set it up as a ratio of voltages, 10,000 to 500, the number of turns in my primary to the number of turns in my secondary. Because this is the primary voltage and this is the secondary voltage. Notice primary goes to the primary, secondary goes to secondary. So if I have a transformer, the primary transformer has 200 turns in it. How many turns does the secondary transformer have to have? Well, it's 500 times 200 divided by 10,000. Ends up being 10 turns, right? But I could have set that up as 10,000 volts to my number of turns in my primary equals 500 volts to the number of turns in my secondary. Notice, again, the 500 in the secondary are still linked, the 10,000 in the primary are still linked. If I put in my 200 turns in my primary, it's still 200 times 500 divided by 10,000. There isn't always just one way to set up these proportions. There's always at least 4 ways to set them up. It's once you put the first number in, all the other numbers have to be in a certain spot. For example, here, let's say I put the 10,000 right here. Once I put that 10,000 volts in here, then I only have 2 choices for the next one. The 500 volts can either go here or it can go here. Can't go here. So let's say I choose to put the 500 volts here. Once you put the second one in, 500, not 5,000. Once you put the second number in, everything else is determined. Because what goes here has to connect to the 500. That's our number of secondary turns. What goes here has to connect to the 10,000. That's our primary turns. So it's the 200 turns. Make sense? There's also something called a Wheatstone Bridge that we talked about a little bit, or a bridge circuit. A Wheatstone Bridge is probably the simplest form of a bridge circuit. A Wheatstone Bridge looks something like this. Where what we have here is, we'll call it R1 and R2 for now. Those two are fixed resistors. This is a resistor that we plug in to get a desired effect. And this is usually a potentiometer here. I didn't draw that symbol really well, but variable resistor. I'll do it like this. I use the arrow through the resistor to indicate that's a variable. Remember, our bridge ratio here is R1 to R2. To balance a bridge, let's do a balancing proportion here. To balance the bridge, what that means, the bridge itself is actually connected across between the two halves of the circuit. If these ratios are balanced, there will be zero current through there. That's what a balanced bridge means. There's zero current through the bridge. So if I have 2,000 ohms here and 500 ohms here, if this resistor is installed as a 4,500 ohm resistor, what does this variable resistor have to be set to balance this bridge? Well, I have 2,000 over 500. Rx has to go on top because those two are both on top. So it's 4,500 here, and this is my variable resistance here. If I cross multiply and divide, what do I get? $1,125. Yep. So 1.125 kilo ohms is what it has to be set at. The reason they use bridge circuits like this, I may have mentioned last week, is because most of these resistors are at very least a 10% error, 10% tolerance. So to balance a bridge using just, or to regulate a current using just resistors is very difficult unless you use a setup like this where you can vary this resistor to get an exact current. Now again, you could have set these up in any order. I could have done the 2,000 over 4,500 if I wanted to. Well, now the 2,000 goes with the 500, so 500 had to go here. X has to go with the 4,500. Notice it's still the same calculation. 4,500 times 500 divided by 2,000. The reason we usually see these proportions always done the same way is because in industry there are standard ratios that are meaningful to us. This is the bridge ratio. Well, since we already have that established ratio, when we set up a proportion, chances are we're going to use that bridge ratio and then set the other ratio equal to it. The same up here. NP over NS, actually technically it's the other way around, usually it's NS over NP, is a transformer ratio. So we would generally use that standard ratio and then set up the other half of the proportion to match it. If I want to have, let's see here. We'll let the highlighted line simulate our transistor core or transformer core here. Let's say that we have an input voltage here of 10,000 volts. 500 turns on the primary coil here. If this coil here has 40 turns, find the output voltage of that transformer for me. See if you can set up that proportion. $800, you're saying? So let's take a look. Typically, we use our transformer ratio of secondary turns to primary turns. So 40 to 500. Where's the 10,000 volts going to go? On bottom. That goes with the primary turns. So 40 times 10,000 is 400,000. Divided by 500 is 800 volts. Any questions? This is what we call direct proportion. Or sometimes called a direct relationship. When one number gets bigger, the other number had to get bigger. The number of turns gets larger, the voltage that's on that side is larger. There are something called inverse relationships. And in inverse relationships, when one number gets larger, the other one has to get smaller, or the other way around. If one gets smaller, the other one has to get larger. We're going to see several of these coming up over the next several days. I mean, today we're going to keep focusing on the direct relationships. But since we brought up transformers, one of them, the voltage may be direct, but here the voltage gets stepped down. What's the trade-off? So the number of turns gets smaller, the voltage gets smaller. What happens to the current? Current gets larger. Because what's the net power have to be from one side to the other? The power in has to equal the power out. Minus some sort of an efficiency loss, right? Usually it's the power in equals an efficiency factor times the power out, if it's a 95% efficient or whatever. But in order to maintain the same power, if the voltage gets larger, the current has to get smaller. Another relationship is our Ohm's law. Voltage equals current times resistance. Well, if the current gets bigger, the voltage stays the same. If the current gets bigger, the resistance has to get smaller, or the other way around. If the current gets smaller, the resistance had to get bigger to maintain the same voltage. We'll look at it with our RPMs and our size of our gears. We'll look at it with pumps. The more cubic feet per minute the pump produces, the time it takes to pump out a flooded pit is going to be less. Stuff like that. So whenever we look at a situation, we have to ask ourselves, is it going to be directly related or inversely related? Let's look at the resistance in a wire compared to the length of a wire. Are those directly related or inversely related? If the wire gets longer, does the resistance get bigger or smaller? Bigger. So they both go up. That is direct. So let's say that we have we're going to look at a packet with resistivity and stuff here in a couple of weeks. But for most of what we have, the constants we have are going to be in meters. So let's say a 200 meter wire has 0.8 ohms of resistance. How would we find the resistance for a 450 ohm or meter piece of wire? Well, this can be set up a couple of different ways. We could set it up exactly like I have it here. The length compared to the length equals resistance compared to resistance. 450 times 0.8 divided by 200 is going to be what? 2.0? 2.0 ohms. We could set it up as 200, actually it'd make more sense to do it as a rate of 0.8 ohms per 200 meters equals blank ohms to 450 meters. Again, you see it's going to be the same calculation. 0.8 times 450 divided by 200. So I don't want to harp on it, but I want to get that point across that there's several different ways a lot of these proportions can be set up. And this is one of them. Since there isn't typically a set ratio for resistance, there's a lot of different ways you'd set that up. Now, I tend to turn it into a rate as a resistance per length and use that as my proportion, as my ratio in my proportion. But you could always, like I said, you can set up length to length, resistance to resistance is going to work well. Some of our proportions we're going to set up deal with measurements. We might have, let's say that there are 16 pounds per 8 feet of, that's 15 pounds, let's make it a little more reasonable. 15 pounds per 8 feet of material. I want to know how many ounces that's going to be for 5 inches of material. Well, obviously, these units are not the same. For this proportion to work, those units must be the same. It's easier to turn the big units into smaller units, so I'm going to do it that way. 15 pounds is how many ounces? There you go, 240 ounces. So I'm going to make that conversion. 8 feet, 96 inches. So now we can cross multiply and divide. 240 times 5 divided by 96. Perfect. That's 12.5 ounces for 5 inches of material. We might have, let's say we're looking at like a sealer where it takes 3 gallons to cover 400 square feet. I want to know how many pints it's going to take to cover that's a bit, 1,000 square inches. So square inches. Again, it's easier to turn the big units into smaller ones. 3 gallons is how many pints? 3 times 4 would be quarts. 12 quarts times another 2 is 24 pints. The big key, 4,000 square feet is how many square inches? It's not times 12. Times 12 times 12, yes. Or 144. Perfect, 57,600. So then we cross multiply and divide, and we get what? It's 2.4, isn't it? Yep, you're right. 0.41. .667 or 67. What do you think? Okay. So in the packet that we did, the measurement packet that has the measurements on front, finish her off. Yep. It says slopes, ratios, and proportions on it. This is the measurement packet. Yeah, it's this one here. This one we just went over. It says slopes, ratios, and proportions. It's the measurement packet. Finish that. Then in another packet you have 2 other packets. It's not the one you have in your hand. It's the other one. That one. Yep, the one in your left hand. I want you to do unit 29 in that packet. So it should be the next unit, I believe. Yep. You do the odds. The odds will be good enough for you to turn them. You guys have the last 10 minutes here to get started on those.